Hello and welcome back to Non-IITN. This is going to be one of the most important lectures of this particular series on group theory, and the reason why this particular lecture is going to be important because in this very lecture we're gonna talk in details about the most important class of groups or the most important examples of groups which you typically come across various competitive exams, and these in some sense give you a lot of wealthy information about groups, about the structure and the inner structure of groups in some sense. And also, since I do not make these lectures strictly node based, so I typically feed these lectures with a lot of extra informations while giving this lecture. So these are extremely important things which you need to keep in your mind. Nevertheless, let's start this lecture. So first we'll talk about a very few important definitions regarding groups which you usually do not come across in standard textbooks or in standard lectures. Okay, so the definitions are as follows. The first definition being that of a divisible group. So it's a divisible group, and the definition is as follows. So an abelian group you need not consider it to be an abelian group in that aspect, but in fact you can just talk about a group in some sense. So let me just precisely be talking about just a group. So group G is said to be divisible if for all x in G and for all positive integer n there exists an element y in G such that y to the power n is equal to x. Okay, so please go through the definition quite clearly, that a group G is said to be divisible if for every element x in G and for every positive integer you will get some element in the group such that y to the power n is x. You can translate it to additive aspect as well. Now something which you can immediately observe from here is that some immediate examples of divisible groups are Q with respect to addition, R with respect to addition, and C also with respect to addition. But so these are examples, and a non-example would be Z with respect to addition, because you obviously know that for Z plus to be divisible, for example, suppose you choose, let's say you choose n equal to 2 and you choose let's say x equal to 1, then you need to have 2 times y to be equal to 1, but that would imply y is equal to 1 over 2, which is not in Z. So you will never get an element in Z which satisfies the definition of divisibility. Are you getting my point? So Z won't be a divisible group, but Q, R and C are. This is a very simple exercise which you can take up from here, that image, homomorphic image of a divisible group is divisible. Okay, and this actually helps you to talk about whether homomorphisms between two groups specifically exists or not. For example, I might ask you a question that, yeah, something more you can talk about here. Also, another exercise, a very simple one, prove that no finite group is divisible, and I'm giving you a hint to solve this. So hint, for every x in G, x to the power order of G would be 1. So this is the hint, and this is the only thing which you need to prove this, that no finite group is divisible. So you cannot have a in some sense a surjective homomorphism from a divisible group to a non-divisible group. For example, you will never have a surjective homomorphism from Q plus to Z plus. This is one way to contradict it. Okay, The next important definition I would like to talk about in this aspect is the notion of torsions. And the definition is as follows. So an element G of a group capital G is said to be a torsion element if it's a finite order. A very simple example, a very simple definition. Okay, and some immediate aspects of it are as follows. So I'm just just bringing out all the relevant definitions in that aspect. So in an abelian group, for example, in an abelian group, the set of all torsions, or you can just take a group. In a group, the set of all torsions forms a subgroup. No, I require this to be abelian, because in a non-abelian group you can take two elements which are of finite order, but still their product need not be of a finite order, so forms a subgroup. Okay, and this is we denote as T of G. So it's the collection of all the elements G in G, such that G to the power n is equal to 1. And make it clear that we are we are talking about it being a subgroup when we are considering it to be a finite order. For example, you can take a group of words formed by two alphabets. You can take both of them to be finite, but you can just keep multiplying them. That won't be of a finite order. Okay, is it clear? So it's necessary that for the torsion group, for the collection of torsion elements to be a subgroup, you need the group to be abelian. So let me just mark them up. The next important example in this aspect would be a group is said to be torsion free. Obviously, sorry, that was the language I would be speaking. Torsion free if the identity is the only element of finite order Okay, yeah. So for example, you can talk about Z plus, Q plus, and R plus. All of these are of finite order. A group is said to be a pure torsion group, a pure torsion group if every element in the group is a torsion element, is the torsion element. So in this case, what you have is by our notation, T of G must be equal to G. And one very important example of such a group is Q mod Z. So this is the collection of all the cosets of the form P plus Q plus Z, P over Q plus Z, such that you can take them to be in the reduced form. Every element here is of finite order. And that quite follows, because you can just multiply it with Q and you will get Z. So that's the identity in the coset. Right? Fine. Yeah, so those are the things which we require for now. And now let me move on to discussion on, so this is a primary discussion on a few very important groups. Now moving on to such a discussion, I would like to speak about something which I do not find very relevant to speak about for at least at this point, but nevertheless it's a good discussion to start with, which is the notion of a group action. I'm just giving a very very subtle discussion about this, because I just thought of talking a little bit about it, because I was talking about inner automorphisms in one of the previous lectures. So if G is a group, so let let G be a group and X be a set. So X is just a set. So we say that G acts on X if there exists a map from G cross X to X such that defined in the following sense, defined as we take two elements and we just write it as G dot X, that is G acting on X, such that it follows the following two properties. Firstly, if I have two elements in the group, so they act on them in the following sense. So G1 acts on G2 and G2 acts on X in the following sense. And the element 1 acts on X trivially. Okay. Now, why is this important? So what I can do is that I can transform this into a homomorphism in the following sense. So, so let G be an element of G, then define phi of G as a map from X to X by phi of G takes an element and maps it to the action of G on X. Okay. Now, what you can typically observe from here is that this actually gives you a correspondence between the elements of the group and the way it acts on the elements of X. Okay. So now let G, so this is something which we write as, so G acts on X. So this is G acts on X. Okay. Now let G act on G. Okay. By, let's say, left multiplication. So this is also called the transitive action probably. Multiplication. Okay, so I wrote it horribly wrong. Multiplication. That is G of X is nothing but Gx. That's it. Okay. So this corresponds to phi of G acting on X as Gx. So this corresponds to this particular thing, and now what you can probably do from here is the following. That is, you can take a map, let's say alpha, from G to the permutations of G. So this is how I typically write it down. So this is the collection of permutations of G, because what something which you can observe from here is that phi G actually permutes the elements of G, right? Because as you know, as you traverse over all the elements G, you will just permute out the elements of G by left multiplying it by each of these elements G from capital G, and you can just take phi of G to be phi G. Now what you can observe from here is the following thing, that is, what is so see, this is typically well defined from the way we have defined it in some sense, right? Yeah. So now observe that alpha of G1 G2 is equal to phi of G1 G2. So it will obviously act on some element X. So this is just G1 G2 acting on X, but then by the property this is just G1 acting on G2X, but then this is nothing but phi of G1 composed with phi of G2, or in our used versions this should be this, which is alpha of G1 times alpha of G2 in terms of composition. So phi is a well-defined homomorphism. Alpha is a homomorphism. Something I forgot to mention, that this need not be a homomorphism in some sense. Okay, so this is just a map. This is a quite an observable homomorphism. Moreover, observe something, that if phi of G is, what is the kernel of alpha? So it's the collection of all the elements G in G, such that phi of G is 1. That is the collection of all the elements G in G, such that, so what does phi of G equals to 1 means? So these are in some sense, so that is phi of G acts on X, it produces X, that is G in G, such that G of X equal to X for every X in X, every X in G. but that would just mean G is equal to 1, so it's trivial, and there's an injective map. So therefore G is embedded in the permutations of G. Okay, so if the order of G is finite, then G is isomorphic to a subgroup of S of G, and this is what you famously call the Cayley theorem. That is, every group is isomorphic to a subgroup of some permutation group. Okay, fine. One more very important example of a group action is G acting on itself by conjugation, and that is in some sense given as phi of G on X is given as G inverse, right? Now in fact this is a homomorphism. So this is a homomorphism, and in fact you can observe that this is in fact an isomorphism. This is in fact an isomorphism, and hence by its name it's an automorphism. And the collection of these automorphisms is what you call inner automorphisms. These are called inner automorphisms. Okay. And these inner automorphisms actually form the collection of all non-trivial automorphisms on non-abelian groups. So every non-abelian group will admit at least one non-trivial automorphism, and those are these inner automorphisms. Okay, fine. There are many more interesting properties of inner automorphisms, which you can argue for in later, but rather let us not talk about those things at this point. Fine. In fact, what I was wanting to discuss is the following. Let me just keep it. So it's the following thing. So if this is the action you have defined, then obviously this again induces a map from G to SG. Okay, and by sigma of G being sent to phi of G, and this forms the collection of all inner automorphisms. So therefore the image of sigma is what we call INNG, the collection of all inner automorphisms on G. And this is a very simple exercise to observe that the kernel of sigma, which is the collection of all G in G, such that phi of G is trivial, this is nothing but the center of the group. So by first isomorphism theorem, G mod the center of G is isomorphic to the inner automorphism group of G. This is also a very important result in group theory. Nevertheless, let us move on to what we were trying to discuss. Okay, now the first thing which I would actually like to discuss is the following, is that the first group I would like to discuss about the group of rationals. Okay, what are the important properties here? The first thing is that so let me just write this. So it's divisible by exactly the structure of the elements in Q plus. Secondly, it's torsion free because none of the elements are of finite order except the identity. This is a very important property, that is, every finitely generated subgroup of Q is cyclic. And in fact, Q itself is not cyclic. That's a very easy proof, and I think I have also proved it in some sense in some previous lecture. That also proves that Q is not finitely generated over Z. The next important thing is that the subgroups in Q are either cyclic or dense in R. The next important property would be Q has no proper subgroup of finite index. And the last important property would be the automorphism group of Q is isomorphic to the set of the set of units of Q. And the reason is very simple. See, you can argue the following, that the if phi if f from Q to Q is a homomorphism, simply is a homomorphism, then f of p over q is of the form p over q times f of 1. So it's a very simple exercise. You can try and do it on your own. Okay, you can just apply, you can just prove this first for all integers, and then you can just use a simple algebraic trick to prove it for the inverses. Nevertheless, what it means that any homomorphism is of this form, f of x equal to c times x. For an automorphism, I need this to be invertible. So this is invertible. Observe that this is invertible if and only if C is invertible. But that means C is a unit in Q, which implies C is in Q cross, the collection of all invertible elements in Q. And so therefore you can characterize the, so you can just take the definition of this to be FC as a automorphism, and you can just take a map phi from automorphism group of Q to Q cross by taking each of these FCs and mapping it to C. So this will give you a bijection, in fact an isomorphism. Okay. So the automorphism group of Q is isomorphic to Q cross. What about the groups R and C? So in R also you have the same property, that every subgroup is either cyclic or is dense in C. So let me just again write them one by one. So both are divisible. Both are divisible. What more can we say? Both are torsion free. Both are torsion free. Yeah, just wait a second. Yeah, so both are torsion free. Let me just remember what are the things which I wanted to say. Yeah, I can also say about the subgroups of R in the following sense, that subgroups of R are either cyclic, so of the form AZ, or dense in R. The automorphism group of R is massive, because it in some sense related to the notion of a Hamel basis with respect to Q. But something which is very important and very non-trivial to say is that the only continuous, or in fact measurable, automorphism on R is the identity automorphism. Okay. Also, these groups have no proper subgroup of finite index, so no proper subgroup of finite index. Now let us move on to the third important group which I wanted to discuss, which is the quotient group Q over Z with respect to addition, obviously. Now the first important property is that it's divisible. The next important property, it's a pure torsion group. That is, every element is of finite order, and I said you the reason why. The next important property is that the number of elements of order n in Q mod Z is phi n, a property typically you see in cyclic groups, is somewhat observed here as well. Okay. Okay. What more can we say? um yeah, yeah, it will do. The next important thing I would like to talk about is that every finite subgroup of Q mod Z is cyclic, and in fact it contains a copy of every finite cyclic group. So it contains a copy of every finite cyclic group. Okay. Now the automorphism group of Q mod Z is highly non-trivial, so I won't be indulging in it a lot, but it's isomorphic to the product of the group of units of ZP ranging over all primes P. Okay. So it has a very famous name. So it's called the group. So basically, it's called the group of units of the profinite group. So the profinite group is basically the product of all ZPs over P ranging over all the primes. Okay. Yeah, let us move on to the next important group, which is C cross with respect to multiplication, the group of units of C. Now the first important thing is that it's divisible, and it's divisible, and this follows from the fact that it's algebraically closed. Or you can just simply say the thing is that in C we know that every element has an nth root, and exactly the reason why it's divisible. The second thing is that the torsion subgroup, that is the collection of all torsion elements, which forms a group obviously because it's abelian. So the torsion subgroup of C cross is the collection of all roots of unity. It's not exactly the collection. Torsion subgroup of it's I should say it consists of all roots of unity, and this collection, the collection of all roots of unity, is in fact isomorphic to the group Q cross C. So Q cross C is actually isomorphic to all the roots of unity in C. Okay. The next important property is that finite subgroups of C cross are cyclic, and it's a general property of all fields, that is the any finite subgroup of the multiplicative group of a field is cyclic. Okay, so what is a field? A field is basically an additive abelian group such that it's every non-trivial element is a unit, and the multiplication and addition, they associate with each other in terms of distribution. We'll come to that in a bit. Secondly, C cross has no proper subgroup of finite order. Okay, fine. Yeah, so fine, let's move on to the next important group I would like to talk about, which is the group of all units of Q, again in terms of multiplication obviously. And firstly, what should I say? It's not divisible. Obviously it's not divisible because every element uh, won't have an nth root. For example, the negative elements, or simply in fact two won't have a 2 is not, does not have a square root, so it's not divisible. The torsion subgroup of Q cross is isomorphic to Z2, and it in fact contains the elements 1 and -1. So these are the only elements of finite order. The next thing is that the automorphism group of Q cross is isomorphic to the group of permutations of the set of all primes in Z. That's a very interesting structure. That is, the automorphism group of Q cross is the group of all permutations of the set of all primes in Z. Now I'm interested in not involving, not indulging the proof of these particular things, because they require a lot of work, and I'm not, in some sense, that much concerned about proving all this stuff, because at some point of your life, if you move on into academia, you will come up with the proofs of all these things, either on your own or in some aspect of it. Nevertheless, at this point, it's not that important. In fact, finite group has a very interesting property, is that in fact not a finite group, in fact any typical group, is that if you have a prime which divides the order of the group, then the group will surely have an element of that prime order, and it's called the Cauchy theorem. You must have heard of it at some point. The last thing which I want to talk about are finite fields. So let me give a very brief description of what a field is. So let f with respect to plus be an abelian group such that we can also define a multiplication on this, or I can just simply say it in the following sense: is an abelian group with a compatible multiplication such that every non-zero element of f is a unit, and for every a, b and c in f, a times b plus c is equal to ab plus ac, and a plus b times c is equal to ac plus bc. That is distribution holds from both sides. Okay, the trivial examples of fields would be q, r, c. All of these are are fields, and zp is an important finite field. In fact, it's a prime subfield. That is, every finite field will contain zp, and it's the smallest field it will all finite fields contain. And q is also a prime subfield of all infinite fields, so every infinite field will obviously always contain q, and these are the only two prime subfields. You will learn more about prime subfields once you study at some point of your life Galois theory or field theory courses. Okay, now obviously finite fields are never, so they are never, so in this context, when I'm talking about groups, so I'm particularly focusing on the the multiplicative structure of it. So I'm talking about fq cross. So it's is not divisible, obviously, because it's a finite group. So fq cross is cyclic because it's a finite subgroup of the multiplicative group of a field, because the field itself is finite. Moreover, the automorphism group of fq cross, it's actually isomorphic to the group of units of zq minus 1, which in our language we have translated as this. Okay, and later in your life we will be able to prove that every finite field has order p to the power n for some prime p. Okay, so the automorphism group of finite fields are isomorphic to the group of units of zq. Okay, yeah. So in some sense we have discussed a lot about the important group structures, and I hope it's a lot about this lecture. In the next lecture, we will be starting with symmetric groups and dihedral groups. I don't think I will be able to cover all of those in one single lecture, but I'll try to cover symmetric groups in a lecture and then dihedral groups in a lecture. And in when we will be studying symmetric groups, we will be covering alternating groups as well in a single lecture. And once we have done this, then the next important aspect of our discussion would be counting homomorphisms. That would be the last lecture of the theory section. The other things we would be discussing in the problem solving sessions. Okay, fine. And then I'll also give a very brief discussion about non-abelian groups, that what are the things which are not trivially holding there and what are the things which you should not expect in a non-abelian group, which you can see happening on a very general note in abelian groups in some sense. Nevertheless, that's all for this lecture. Meet you guys in the next lecture.